It's now my honor to introduce Mike Clancy. Among many other things in his professional life, Mike was the technical and scientific director of the United States Navy's Fleet Numerical Meteorology and Oceanography Center from 2005 to 2011. And in addition to that, he was also the recipient of the Navy's highest civilian award. With that said, I will turn this over to Mike, who will address understanding and mitigating climate change. Welcome, Mike.
Oh, thank you so much, Sis. I want to begin by particularly thanking Jay and Delon Gentry for kind of starting this whole idea out. I also want to thank Peyton Trim for helping getting set up, but most of all, I want to thank Sis Conley for making this happen. Now I'm going to share my screen because we're going to be looking at a lot of PowerPoint slides here. So hang on here with me for a second. And you may want to be in speaker view if you want to be watching me talk while you're watching my slides, or you can select a gallery view if you want to see the other people on the talk here. But it's most important that you see my slides. So quick outline, introduction and context. We're going to talk about what's causing global warming and climate change. We're going to talk about greenhouse gases, global consequences, global warming projections to the end of the century, what needs to be done. I'll have some closing comments, and then I'm happy to stay around as long as people want to stay around for question and answer. Got to warn you up front, I tend to talk fast, I tend to move fast, and I'm going to be showing you a lot of technical material. If it's not making sense to you, if you're not sure what I'm showing, please unmute and stop me so I can explain it. But I'll also, of course, be answering questions after the talk. So let's jump right in on introduction and context. I want to begin by showing you this plot of global mean surface temperature of the Earth over the past 22,000 years. So 0 here is the present time. And the left-hand part of the chart here is 22,000 years ago. Now, surface temperature over the ocean is the sea surface temperature. Over the land is the temperature a few meters above the surface. And global mean implies averaged over the entire face of the Earth. So put this in context. To put this in context, here is the beginning of human civilization about 9,000 years ago. This is the last ice age. And this warm period here, colored in blue, is called the Holocene warm period or interglacial period. All of human civilization has been played out from this point on here. Now, this period of warming here was the recovery from the last ice age. And that was driven by something called the eccentricity cycle. So we're going to now talk a little bit about what drives the ice age cycle. Now, I'm sure you all know that the Earth orbits the sun in an ellipse, such that in Northern Hemisphere summer, the Earth is farther away from the sun than it is in Northern Hemisphere winter. That's good for us who live in the Northern Hemisphere because that makes our summers cooler and our winters warmer. But what you may not know is this ellipse is not constant in time. It fluctuates back and forth from being more drawn out like an ellipse to less drawn out and flattened more like a circle on a 100,000 year cycle. That cycle is driven by the gravitational pull of Jupiter and Saturn on the Earth. Now, it's highly exaggerated in this figure. It's actually only about a 1% variation, but it's enough to have a profound impact on the Earth's climate. And in fact, that's exactly what drives the ice age, the 100,000 year ice age cycle we've been experiencing, the Earth has been experiencing for the past million years. As the Earth draws out into more of an elliptical orbit, that tends to drive us into an ice age. As the orbit flattens back out, being more circular, we come out of the ice age. So what was happening during this 10,000 year period? The orbit of the Earth was coming more like a circle, and so there was a warming trend here, and we came out of the ice age into the Holocene interglacial period, and along came human civilization. Now, the next thing that's obvious on this is this slow cooling trend during the Holocene period here. And that cooling trend, in fact, is driven by what's called the obliquity cycle. And I'm sure you all know that the Earth's axis is inclined relative to the plane in which it orbits. That's, of course, what gives us the seasons. In Northern Hemisphere summer, the North Pole is tilted towards the sun. But what you may not know is this tilt rocks back and forth in time on a 41,000 year period, driven by the gravitational effect of the sun and the moon on the Earth. We're about halfway through the cycle right now, and we're losing tilt. We've been losing tilt for about the last 7,000 years. We've lost about a half a degree of angular tilt over the last, or a little more, over the last 7,000 years. And that's given rise to this slow cooling trend as we're heading towards, under normal conditions, heading towards the next ice age in about 8,000 years. Now, there's a couple of other things that are apparent on this slide. This is about a 1,500-year interruption of the warming trend coming out of the ice age. Is called the Younger Dryas period. This little bump here is called the medieval warm period. That was from about 900 to 1200 AD. And this is called the Little Ice Age from about 1500 to 1700 AD. And finally, we come to this red spike. This red spike is, in fact, the post-industrial global warming that we are concerned with. Now, there are two things that become apparent when you see it in this context. First of all, it's going in the wrong direction. We should be cooling. The obliquity cycle we talked about should be causing, it has been causing a slow cooling of the Earth for the past 7,000 years, but suddenly we're warming. We're going in the wrong direction. We should be heading towards the next ice age, but we're going in the wrong direction. The other thing is we're going really, really fast. In fact, the warming we're seeing here is about 20 times faster than natural climate change. This is what natural climate change looks like. It's a very slow trend here. This is what unnatural climate change looks like, human-induced climate change. It's going 20 times too fast in the wrong direction. That's the main reason we know this is not natural climate change. Now I'm going to zoom in again on this red spike here. So now we're going to be looking at the 170-year view. We're going back about 170 years to 1850. And again, we're looking at the same parameter we looked at before, global mean surface temperature of the Earth, just as before. But now we're looking at it from 5 different sources, and those sources are listed here. And I won't go into details about what each product is built on, but I can tell you they all involve surface data from ships and from weather stations and all that. Some of them involve satellite data as well. So some also include weather balloon data, upper air data. Some of them include computer models and very sophisticated statistical techniques for assimilating data. Others just handle the surface data in a very simple way. So 5 independent groups, 5 independent data sets, 5 independent approaches to the data, and they all paint the same picture. And that picture is as follows. From 1850 to 1880, not much going on, kind of going sideways, a slight decline from 1880 to 1910, pretty strong upward rise from 1910 to 1945, slight decline from 45 to 75, and then beginning in about the mid 70s, there was a strong upward movement of the temperature such that we are now running about 1.2 degrees centigrade above the pre-industrial level. Now, a couple of things about this. Notice the very close agreement, particularly here in the modern era, between these 5 different independent groups. That means that tells you we have a lot of confidence in this picture. And also it tells you that the climate system is very well observed. We have more data than we need. We could throw away tons of data. We've got plenty of data to observe the climate. That's because the data set observing the atmosphere and the ocean is really geared toward the weather prediction problem as opposed to the climate problem. And as a result, the climate is oversampled. So we have a very good handle on the climate. That's the first thing. The second thing is, notice that it doesn't go up in a straight line. There's all these zigs and zags here. It's kind of like the stock market. You know, the stock market doesn't go up in a straight line. It goes up over the long term, but it doesn't go up in a straight line. There are zigs and zags, volatility. And that's the same thing that happens here. This volatility, so to speak, is these zigs and zags, are a result of what's called climate variability. That's things like El Nino and La Nina, things that affect the global mean surface temperature of the Earth as heat is exchanged between the atmosphere and the ocean on timescales of months to decades. That's different from climate change. Climate change is the longer term trend, 30 years or longer. If you're looking at something that's a record of temperature or what have you, that's 20 years or shorter, you're not looking at climate change. You need to be looking at a record that's 30 years or longer. You need to look at those longer trends. Between 20 and 30 years, that's kind of gray area, but kind of overlaps, but you really like to be looking at closer to the 30-year end of that spectrum. Now, I'm going to show you an animation of one of these. In fact, I'm going to show you an animation of this one here, the NASA product. And what we're going to be looking at is a map of global temperature anomaly from 1880 to 2018, a time sequence of that over the entire face of the Earth here. Now, temperature anomaly is just a fancy way of saying temperature difference from a reference field. And in this case, the reference field is the 1951 through 1980 average. So we form that average over that 30-year period. And then year by year, we form the difference of that, and that's the so-called temperature anomaly. Now, here's the scale right here. Where where you see white shading, that means the temperature is the same as this 30-year average. Where you see yellow to orange, it means it's warmer. Dark orange is 2 degrees centigrade warmer. Where you see blue, it's cooler. Dark blue is 2 degrees centigrade cooler. So we'll see how that evolves. Now, a couple things about this data set. First of all, it's a lot of data over the ocean. It's about 350 million observations from ships, and in recent years, drifting buoys and moored buoys and things like that. Over the land, it's basically the weather stations that occur all over the world, and there's about 2 billion observations during this period. A couple things you might be aware of. You might have heard about the urban heat island effect. That's a real effect. Cities are sort of unusually warm because they trap heat in all the concrete and the asphalt and so forth. Don't worry about it. That's been taken out. There's about 300 stations that were deemed to be contaminated by urban heat island effect. Don't worry about it. Taken out. You might be aware that in the first half of the 20th century, ships made sea surface temperature measurements with the bucket technique. They actually threw a bucket over the side with a rope on it, pulled it back in, stuck the thermometer in that water, and measured the sea surface temperature that way. In the second half of this 20th century, they made a transition to engine room injection temperatures. And the reason I'm bringing that up is there's a bias between those. The bucket temperatures were biased cooled by about a tenth of a degree centigrade or two, and the engine room injection temperatures are biased warm about 2/10 of a degree centigrade. So that's actually pretty significant in terms of climate trends. Don't worry about it. Correct it out. Not a problem. You might be worried about computer models. You know, these computer models, what the heck are they all about? Well, don't worry about it. There's no computer models here at all. No computer models involved in what I'm going to show you. You might be worried about satellite data. Satellites are kind of tricky. It's tricky to extract information from satellite data that's relevant to climate. Don't worry about it. There's no satellite data here. This is pure in situ data. That's data taken in place. About 350 million observations over the ocean, about 2 billion observations over land. So it's a really very good data set. So I'm going to roll this video, and I'm going to call out the decades. So you focus your attention on the patterns as they're changing. Pay particular attention to what happens in the 1970s, and when it stops, we'll draw some conclusions here. So here we go. 1880s, 1890s, 1900s, 1910s, 1920s, 1930s, 1940s, 1950s, 1960s, 1970s, 1980s, 1990s, 2000s, 2010, and we end up at 2018. So what you can see here is a couple things. First of all, the land is warming faster than the sea, but the sea is certainly warming. Look at all the yellows over the sea. Land is warming actually about twice as fast as the ocean. But the ocean actually is actually absorbing about 95% of the heat, and thank God for that, because if it wasn't for the ocean absorbing all that heat of global warming, the Earth wouldn't be livable by humans. The temperature of the atmosphere would be about 70 degrees Fahrenheit hotter than it is now, and it wouldn't be livable by humans. Thank God for the oceans absorbing about 95% of that heat. But why is the ocean not warming? It's because the ocean has tremendous heat capacity. It has a tremendous capacity to absorb heat, much more than the land and the atmosphere. So it's both a blessing and a curse. It's a blessing because it gives us a livable planet, but it's also a curse because, number one, as the ocean's warming, it's causing problems for fisheries. It's causing oxygen levels to go down in the ocean. It's causing a big problem for coral reefs. You've probably heard about coral bleaching. So-called ocean heat waves are the primary cause of coral bleaching. But also, when future generations in the next century, not just this century, the next century, try to cool the Earth back down, and they're going to have to cool the Earth back down. That's going to be hard because there's a tremendous amount of heat that's going to be that is stored in the ocean that will be slowly given back up, and that's going to be difficult, make it difficult to cool the Earth down. Other thing that's obvious here is that as you go farther north, the warming increases. In fact, the Arctic is warming about 2 to 3 times faster than the global average, and that's not a good thing because, of course, the ice is melting up there, and that contributes to the ice sheets anyway, and the glaciers melting contributes to sea level rise. Notice that the western 1/4 of North America, where we live, is warming quite a bit faster than the eastern 3/4. The western US has warmed quite a bit faster. And oh, by the way, with that warming has come drying, and that's a big problem for us in terms of wildfires and that sort of thing. We'll talk about that a little bit later. And then finally, notice that it's not warming everywhere. There are areas where it's actually cooling, for example, in this region here. And there are regions along the edge of Antarctica, and there are other regions in the middle of the Pacific that actually has been cooling rather than warming. So that's when we say, when we talk about global warming, you need to talk about the global picture. You can find places where it's warming at only a small amount or maybe even cooling, but that is not a proxy for the global picture. When you talk about global warming, you need to talk about the global picture. So what's causing that global warming and climate change? Well, in fact, it's the greenhouse effect, which I'm sure you've heard about. And to really understand the greenhouse effect, I'm going to take you a little bit deeper than, I imagine all of you are pretty familiar with the greenhouse effect, but I'm going to take you a little bit deeper into the science of it. So hang in there with me. And the way to really understand the greenhouse effect is to look at the Earth's energy budget, which is depicted here. And what this shows is incoming solar radiation. Some of it reflects off clouds and aerosols and goes back out to space. Some is reflected off the surface, particularly snow and ice, goes back out to space. Some is absorbed by the land and warms the Earth. Some is absorbed by the atmosphere. And then the Earth is cooled by outgoing long-wave radiation, also known as infrared radiation, and it is emitted by the surface. It's absorbed by clouds, absorbed by the atmosphere. Some goes directly out to space. Some is emitted by the atmosphere. Some is emitted by clouds. But a large amount of it is trapped by greenhouse gases and comes back as back radiation. So 396 units go up, and 333 come right back down as a result of these greenhouse gases. So about 85% of the long wave radiation that's trying to cool the Earth is actually radiated back down, warming the Earth. Now, one question you might have is, what about other sources of heat? Why aren't they depicted on here? For example, what about heat from the Earth's interior? Well, it's really, really small. It turns out it's extremely small compared to the net heat absorbed by the ocean, about 70 times smaller. What about warming due to tidal friction? You know, the tides are moving around, driven by the moon, and what about the energy and the warming from that? It's hundreds of times smaller than the numbers here. Anything you can think of, you know, waste heat from buildings, volcanoes, what have you, really, really small compared to the numbers on this slide. This really is the ballgame. This is what drives the Earth's energy budget. So how does it work? Well, the greenhouse effect works like this. It's pretty straightforward. Incoming solar radiation warms the Earth, the way we were just talking about, and the Earth is cooled in two ways: by reflected solar radiation going back out to space, and the outgoing long-wave radiation going back out to space. And greenhouse gases trap the outgoing long-wave radiation and warm the lower atmosphere and surface of the Earth. Notice that I've underlined lower atmosphere. We're going to come back to that in a minute. Now, and finally, human activities increase greenhouse gases in the atmosphere and increase the warming. So what are these greenhouse gases? Well, I've kind of put them in order here and how much infrared radiation they trap. Top of the list is water, H2O, water vapor, which we of course perceive as humidity. And then comes CO2, carbon dioxide, methane, the F gases, or the fluorinated gases. These are man-made gases that are used in refrigeration, in air conditioning, solvents, and gaseous insulators, that kind of thing. And finally, nitrous oxide, which is a byproduct of agriculture and nitrogen-based fertilizers. Notice that I've colored water vapor differently here, and that's because water vapor, although it traps more infrared radiation than any other of the greenhouse gases, it does not drive global warming. That's because water vapor, for two reasons. That's because, number one, water vapor is in balance with the natural cycle, the natural hydrologic cycle. And number two, water vapor has a very short residency time in the atmosphere. So imagine we could suddenly put a huge amount of water vapor into the atmosphere. What would happen? It would just rain out. It would just fall out within a week or so. The rainfall would take it right back out, and the water vapor would be once again in balance with the natural hydrologic cycle. Suppose we put a bunch of CO2 in the atmosphere, a huge amount of CO2 in the atmosphere. Well, it's going to be there for about 100 years. In fact, even after 1,000 years, you're going to still have about 15% of that CO2 in there. So it's a long-lived greenhouse gas. It's not in balance with any natural cycle. And the same is true of these other gases. That's why they, in fact, are the greenhouse gases that drive global warming. Now, in addition to that, I'm going to take you a little bit deeper into the science and talk about some feedback effects. There's something called the snow ice feedback effect, and it works like this. As the Earth is warming, that causes decreasing snow and ice as snow and ice melts. And you can see that from the picture here, the sea ice is very reflective. It reflects the sun back out to space, sunlight back out to space. That has a cooling effect. But when it melts, what's left behind is a much darker ocean, which absorbs that solar radiation. And that increasing sunlight being absorbed warms the Earth further. Well, that increases the temperatures more, which decreases the snow and ice as that more of it melts. And you just basically go around this feedback loop and you keep amplifying the warming. The snow ice feedback effect, like any feedback effect, does not drive the warming, but it amplifies the warming. And it works the other way around too. If we're suddenly driving the Earth to cool from those orbital effects we talked about earlier, the sun, the moon orbit, or this, the Earth orbiting around the sun and that ellipse changing, then you'll just go around the feedback loop in the opposite direction. It will amplify the cooling. So that's the snow ice feedback effect. And there's also the water vapor feedback effect, and it's pretty straightforward. Again, as you have increasing global temperatures, that produces increasing evaporation of water from both the oceans and from plants on land. And that increases water vapor in the atmosphere, which, because water vapor is a strong, powerful greenhouse gas, that yields increasing global temperatures. And again, you go around this feedback loop and that amplifies the warming. In fact, those two feedback loops together, water vapor feedback, snow ice feedback, amplify the warming by a factor of about 3. If it wasn't for these feedback effects, we would only have seen about a third of the global warming we've experienced. Now, I can't see you on screen. I can only see my slides, but I know what you're thinking, and I can see the look on your face. If I was looking at your faces, I'm sure I'd see it. You'd be saying, well, Mike, this can't be right, because this would be an unstable system. It'd be like trying to balance an ice pick on the tip. You just can't balance it, because once it starts to nudge over to one side, there's a positive feedback gravity that causes it to fall over. It must be unstable. Well, it turns out it is in fact stable, and quite stable. And the reason is there's a very powerful negative feedback, and that's called the long wave radiative feedback. Now, this is the only equation I'm going to show you, so don't get mad at me. This is just one equation here, and it says the outgoing surface radiation is proportional to the temperature to the 4th power, or temperature is called is measured in degrees Kelvin, which is the absolute temperature scale. 0 is at the absolute 0 here. And what that means is, as the Earth warms up just a little bit, the outgoing radiation increases pretty fast because of this temperature to the 4th power effect here, and it tries to cool the Earth back down. If the Earth starts to cool down, the outgoing radiation is reduced and it tries to warm the Earth back up. So it's like a spring, kind of trying to keep things stable here. The problem is we keep nudging this system out of balance. The Earth climate system actually is quite stable if the forcing factors remain constant. Forcing factors are aerosols in the atmosphere, particularly aerosols due to volcanic eruptions, the sun, how brightly the sun is burning, and that varies over time with sunspot activity. And then finally, the greenhouse gases in the atmosphere. If all those were held constant, then the Earth would come into equilibrium and balance in probably a couple of decades, and we would no longer warm, we would no longer cool, we'd be in balance. The problem is we keep nudging it out of balance because we keep putting more and more of these greenhouse gases into the atmosphere, and that keeps nudging the system out of balance, and we keep warming. Now, this is not just me saying all this. What I'm presenting to you is an overwhelming international scientific consensus on this matter. And that is summarized pretty nicely by this partial list of leading science organizations that have made formal declarations confirming human-induced global warming exactly along the lines of what I've described to you. And that includes, for example, the US National Academy of Sciences, the US National Research Council, all the most prestigious science organizations in the world will tell you exactly what I've been telling you. And in fact, there is an overwhelming international scientific consensus on the following 3 points. Point 1, over the past 120 years, the Earth has been warming and the climate has been changing at alarming rates. Number 2, This global warming and climate change has been driven almost exclusively by the accumulation of greenhouse gases in the atmosphere caused by human activities. Number three, without dramatic reduction in the emission of greenhouse gases into the atmosphere, the Earth will continue to warm and the climate will continue to change to the detriment of humankind. So to summarize, number one, it's happening. Number two, humans are causing it. Number three, it's not a good thing. So let's talk about these greenhouse gases that are causing this problem. And here is a list of, again, the long-lived greenhouse gases. Carbon dioxide, methane, also known as natural gas, the same natural gas we have in our homes that power the hot water heaters and so forth. The fluorinated gases, I mentioned briefly, and finally nitrous oxide. And what you see here is that carbon dioxide is the dominant driver of global warming. Not to imply that we don't need to worry about these other gases, we do. Particularly the fluorinated gases. Fortunately, there's not a lot of them in the atmosphere right now, but they are very, very powerful greenhouse gases, and they are very long-lived. Once they get in the atmosphere, they're going to be there for tens of thousands of years. So there's a big problem in the long term if we don't control the fluorinated gases. Very important. But in terms of where we are right now, carbon dioxide is the dominant driver of global warming. So let's take a look at carbon dioxide in the atmosphere from 1700 to 2019, and that's plotted here. And you can see that in the pre-industrial level, the concentration of CO2 in the atmosphere was at about 280 parts per million. That's what we measure concentration. And now it's up around 450 parts per million. We're up here. And that's about an increase of about 50% over the pre-industrial level. Now, the total mass of CO2 in the atmosphere is also of interest. Over this period, the total amount of CO2 emitted by human activities amounted to about 1.6 trillion tons, not billion, trillion, 1.6 trillion tons. And this increased the CO2 in the atmosphere by about 0.9 trillion tons. So we're almost a trillion, we have almost a trillion tons of CO2 up there in the atmosphere now that didn't exist there before the Industrial Revolution. And finally, the current rate of CO2 emission in the atmosphere globally due to human activities is about 40 billion tons per year at the current time, and it's going up. So where's the CO2 coming from by country? Well, China is clearly the number one emitter. These are CO2 emissions by percent of total. United States is number two. United States and China together account for about more than 40% of global CO2 emissions. Then it's India, Russia, Japan, Germany, and on down the list. In terms of per capita emissions, you simply take the total emissions by country, divide by the number of people in that country. Well, there's a lot of people in China, so they drop way down the list, and the United States becomes number one. Although we're followed pretty closely by Australia and Canada, and then it kind of drops on down here. So 16.5 metric tons, that's a little more than a regular ton. And what this chart says is the average American puts about 16.5 tons of CO2 into the atmosphere every year. It's actually a pretty good news story for California. California's carbon footprint is only 9.2 metric tons per person per year, which is significantly better than the US national average. And it puts us down here pretty much somewhere between Germany and Japan. So where is that CO2 coming from in the US? Now picture is just for the United States. It's not the global picture. The global picture is somewhat different. But in terms of the United States, in terms of the impact of greenhouse gas emissions on global warming over the next 100 years, and you calibrate that for the other gases in terms of something called CO2 equivalent. Again, what we see here is that CO2, in fact, is the dominant greenhouse gas. Not only is it the most strongest driver of warming at the current time, we're also emitting more CO2 in the atmosphere in terms of its impact over warming of the next 100 years than any of the other gases. And the vast majority of US CO2 emissions come from these three sectors. First and foremost, transportation, followed by electricity generation. That's basically energizing the power grid, followed by industry, and that's mainly steel and cement production. And these are the big three in terms of US emissions. Globally, transportation is actually pretty low on the list. But in the US, we drive a lot of cars. And as a result, that's our number one source of emissions. So where does all that CO2 go? Well, depicted in this slide here is something called the natural carbon cycle. And I'm not going to take time to go through it. And oh, by the way, I'm going to make my slides available to CIS if people want to get a hold of them. I'm also going to be putting this talk on YouTube so you can go and see it and slow it down and stop if you want to look at more detail. So I'm not going to go into great detail here. I want to just cut to the chase. And basically, in terms of the CO2 emitted by humans, about 30% is taken up by the land, and that's really good. That's what we want. It's sequestered into the soil. You can see it right here through the roots of trees and plants, and that's what we want. About 20% is taken up by the ocean, and that's kind of a double-edged sword. It's good because it's not getting into the atmosphere, but it has a negative impact on the ocean. You've probably heard the term ocean acidification. As CO2 is absorbed into the ocean, it's making the ocean trend more towards the acidic side on the pH scale. If you think back to your high school chemistry, the ocean is still actually on the basic side of neutral, but as CO2 is more and more absorbed into the ocean, it's trending more towards the acidic side. And that causes a real problem for the larvae of shellfish. It causes a real problem for coral reefs, and that's a big problem. And finally, the remaining 50% is accumulating in the atmosphere. And that's why we see that curve of CO2 going up and up, and why we have this problem with global warming. Essentially, we're putting CO2 into the atmosphere about twice as fast as the natural carbon cycle can take it out. And as a result, it's accumulating into the atmosphere. So what are the consequences of this? So I'm not going to go into all the details here. I'm just going to kind of hit the high points. And I like to divide the impacts into two categories: impacts on the natural world and impacts on humans. So this is the natural consequences of a warming world. Increasing frequency and intensity of severe storms, severe weather, increasing frequency of life-threatening heat waves. Oh, by the way, more people globally are killed by heat waves than any other weather phenomenon by far. Not true in the US, but it is true globally. Increasing frequency and intensity of floods in wet regions, increasing frequency of droughts and wildfires in dry regions. Oh, by the way, we live in a dry region, and this is something we can expect to have happen more and more. Decreasing mountain snowpacks and earlier snow melt. And of course, that's a big problem for California, as we get a lot of our dry season water from snow in the Sierra. Rising sea levels, big problem for coastal communities like our own community. Increasing mortality of coral reefs, that's called coral bleaching. Decreasing productivity of fisheries, and loss of biodiversity. Now, I want to highlight a couple of those in a little more detail. And the first is the issue with severe weather. And to understand what's going on there, I want to show you this slide, which depicts the vertical structure of the atmosphere. And there are these different layers of the atmosphere. The lowest layer is called the troposphere, stratosphere, mesosphere, thermosphere. The troposphere is where the weather occurs. And to put it in context, there's a little plane here. If you're flying in a jet airliner at maximum altitude, you're flying right about here. The pilot will say, I want to climb and take you above the weather, where you're going right about here, just a little bit above where the weather is, at the lowest layer of the atmosphere, the troposphere. And the point is, the warming that's occurring is occurring in the lower half of the troposphere, from about the surface up to about 20,000 feet. And that's what I've depicted here in red shading. But everywhere above that, it's actually cooling. Not warming, it's cooling. Why is that? Well, it's because the heat that would normally warm the upper part of the atmosphere is being trapped below. So that's making the atmosphere more unstable. What you're doing is you're warming the atmosphere from below, cooling it from above. Warm air rises, and in fact, it's that warm air rising into cool air that produces the kinetic energy of storms. So as the warming proceeds, as the lower atmosphere gets warmer and warmer, as the upper atmosphere gets cooler and cooler, you're making the atmosphere more unstable. And that's a recipe for more frequent and more severe weather, more frequent severe weather and more severe weather. But at the same time, you're also making the atmosphere more humid, and we talked about that before, as the oceans are warming. And there's more evaporation from both the oceans and the land. That's making the atmosphere more humid. And when clouds occur and moisture is condensed into clouds, that gives up heat. It's called the latent heat of evaporation. And that heat causes the warm air to rise even faster. That's, the main driver of hurricanes. So as we make the atmosphere more humid, that also makes it more unstable. So the bottom line is these changes are fueling increasingly strong storms and severe weather. And you can see that in this slide, which shows trend lines over a 30-year period here of severe storms, severe floods, heat waves, droughts, and wildfires. And you can see they're all trending upward. Now, notice when I say severe storms here, I'm not just talking about summertime storms. I'm not just talking about hurricanes and tornadoes. This includes wintertime storms and blizzards like we're experiencing right now in the central part of the country. So, the warming can produce, can produce the kind of freezing conditions we're seeing now in Texas, because the wintertime storms are getting stronger as well, just as summertime storms are getting stronger because of this increasing instability of the atmosphere. So when you see these tremendous cold outbreaks like they're experiencing in Texas right now, that's not something that contradicts global warming. In fact, it's something that in perhaps counterintuitively confirms global warming, because it shows that the storms are getting stronger. And as the wintertime storms get stronger, you get these more severe cold outbreaks. The other thing I want to talk about briefly is sea level rise. What we're looking here is a plot of global mean sea level rise in millimeters on this side, and 8 inches up here, from 1900 to 2015. The part in blue here is from tide gauge data, and the part in green and orange here is from satellite altimetry data. There are these satellites that can measure sea level from space. And what you can see from 1900 to 2015, the global mean sea level has gone up by about 8 inches. But the thing that's really troubling here, if you look at this curve, you can see that as an upward curve to it, upward bend, it's accelerating. So the sea level rise is accelerating. And it's accelerating mainly because the ice sheets, the Greenland ice sheet and the Antarctic ice sheets, are starting to melt faster. And that's a real problem. Particularly after 2050 is when we see real problems. That's when sea level is expected to rise much more rapidly than it is now. There's a couple things about sea level rise. There's a lot of uncertainty about sea level rise. Right now, predictions are about 1 meter sea level rise between now and the end of the century globally. But it could be as high as 2 meters. There's a lot of uncertainty. When we look back at the predictions that have been made over the last 20 years or so, they've typically underestimated how fast the sea level is rising. So there's the possibility that it will be much more of a problem than we think it's going to be, and it's going to be a problem for sure. So sea level rise is an issue. Now, in terms of human impacts of the warming world, increasing economic costs, increasing competition among nations for water and food, increasing displacements of people and unrest in populations susceptible to recruitment by violent extremist groups, increasing threats to human health, increasing human mortality from heat waves, other severe weather events, starvation, disease, and war. Not a pretty picture, not a pretty picture. Basically, climate change is putting pressure on the basics of life: food, water, and living space. For example, sea level rise. A sea level rise of 1 meter will displace about 100 million people around the world, 30 million in Bangladesh alone. So where are those 100 million people going to go? For example, where are those 30 million people in Bangladesh going to go? Well, they're not going to go to India. They're not going to go to Myanmar. Where are they going to go? So, we're looking at the strong likelihood of humanitarian crises around the world, instability, and, lots of problems involving conflict between nations. So where are we going by the end of this century? So I'm taking you back to the 22,000 year look again. And here's where we are right now on this red spike. In terms of where we may go, if the world fully embraced the recommendations of the Paris Climate Accord to achieve net zero greenhouse gas emissions by 2050 and near zero greenhouse gas emissions by 2100, then we would hold global warming at the end of the century to about 1.5 degrees centigrade, plus or minus 0.7, because there's some uncertainty here. That's where we would be. by the end of the century if we were to achieve that goal. Now, what does this mean, by the way? Net zero greenhouse gas emissions by 2050. What that means is um, we're putting no more greenhouse gases into the atmosphere than the natural world is able to take out. And that means we need to reduce CO2 emissions by a factor of about 2 or 3 by 2050. And that's a pretty difficult thing to achieve. Near zero means we're almost down to zero by the end of the century. And that's where we would need to be if we were going to achieve this 1.5 degree aggressive target for the Paris Accord. Here's where we're going if we adopt business as usual greenhouse gas emissions. Now, business as usual is the term used to imply we just don't do anything. We just throw up our hands, we pull out of the climate accord like we did 4 years ago. And the whole rest of the world does the same thing and nobody pays any attention to this. We just do business as usual. Well, in that situation, we'd be going way up here, 4.5 plus or minus 1 degree. Now look how radical that is. That is as large as the difference between the last ice age and where we are now. It's huge, and the problem is, you can see it here, over the course of human civilization, this is how basically the climate has changed and the temperatures have changed. It's been very, very gradual cooling. And I'll suddenly have this radical spike here. And the question is, can human civilization adapt to something changing so fast? And the answer is probably no. But the good news is we're not going there. We're doing much better than that, but not super great. This is kind of where we're looking at right now. And this is based on very recent information. About once a year, the UN essentially releases what's essentially a report card on how well the world is doing on achieving the goals of the Paris Accord. And the last report card came out just a couple of months ago, and it said basically we're on track for 3 degrees C of warming, which takes us to right about here. That's twice what we were hoping to achieve with the Paris Accord. So that's not a good story. Quite frankly, a lot of that has to do with the fact that the U.S. pulled out of the Paris Accord 4 years ago. And without U.S. leadership in there, other countries say, well, heck, why am I going to make these sacrifices if the U.S. is not going to play? And so every country started falling far behind. I think we're going to do better than that. This is my personal prediction. We'll have to wait around for about 80 years to see if I'm right or not. But this is what I'm thinking we're going to do. I'm thinking we're in the range of about 2.5 degrees C, which is, not great, but it's certainly a lot better than where we could be. My optimism here is driven by the fact, of course, that the U.S. has rejoined the Paris Accord. The Biden administration has asked for $2 trillion in funding over the next 4 years to address climate change, and that's very significant. Whether or not Congress is going to agree to that is unclear, but nevertheless, we're setting an example for the rest of the world, and I think the rest of the world is going to perk up on that, and we'll try to get back on track. So what needs to be done? Well, I strongly recommend something called a Project Drawdown, and you can find them on the web at drawdown.org. Project Drawdown is a nonprofit organization that proposes, analyzes, and ranks solutions for reducing greenhouse gases in the atmosphere. And it was founded in 2014 by noted environmentalist Paul Hawken. They present about 80 solutions. They may be up to 100 solutions now. For avoiding emissions and or sequestering carbon dioxide already in the atmosphere. And these solutions consist of technologies, practices, and policies organized into 9 sectors and implemented in 2 scenarios, essentially providing a roadmap for stopping and eventually reversing global warming and climate change. It's pretty much a technological roadmap for the governments of the world and how we need to proceed. And the great thing about it is, not only do they present the technologies, but they price them out and they rank them in terms of how much carbon dioxide they can remove or avoid emitting. And I personally think they've done a really great job. We could spend hours talking about everything there. Don't have time to do that. So I'm just going to quickly give you an overview. These are the 9 sectors. Electricity has things like, solar and wind power and ways to get off fossil fuels. Food, agriculture, and land use, trying to reduce the emissions from agriculture. Industry, trying to find more efficient ways of doing steel and cement production, that sort of thing. Of course, transportation, more moving to electric vehicles, more efficient ships and airplanes and so forth. Making buildings more efficient. Health and education has to do with trying to hold down global population growth. Land sinks, taking care of our forests, taking care of our rainforest, stopping deforestation, replanting trees, taking care of coastal wetlands. That's here at Coastal and Ocean Sinks, taking care of mangroves, swamps, and coastal wetlands and so forth. Engineered sinks, kind of a new area they're working on. These are technologies that are being developed to actually use man-made technologies to remove carbon dioxide from the atmosphere. So I strongly recommend Project Drawdown. And one of the really good things about them is the fact that they have figured out the costs. They've actually priced out these things. And two scenarios. Scenario 2 is basically achieve the 1.5 degrees C target of the Paris Accord. And then there's a lesser target from Paris, which is 2 degrees C. So they've priced out what it would take. So the annual cost for the world over the next 30 years to achieve the 1.5 degree target would be about $1 trillion a year, which is about 1.25% of global GDP. But the kicker here is there's a return on investment. In fact, over that 30-year period, you would save about 4.8 trillion, which was really pretty good return on investment. In terms of what the price to the U.S. would be, if you prorated these costs according to GDP, and that's a big question as to whether that's really the way you would do it, but if you did do it that way, then the U.S. part of that bill would be $250 billion a year over the next 30 years. Now, the Biden administration has asked for 2 trillion over 4 years, which in fact is twice this. That's 500 billion a year for the next 4 years. So if that gets through, that's a great start here. And the kicker is there's a significant return on investment over the 30-year period. You actually be saving about 1.2 trillion a year. So big numbers, big problem. But these are the things we need to do. And one thing I want to quickly mention in passing. There's a lot of controversy about subsidies of the oil industry. If you ask the oil industry about subsidies, they're going to say very minimal. We hardly get any subsidies. Don't worry about it. If you talk to environmentalists, they're going to say they get huge subsidies, trillions of dollars a year. I consider the IMF, the International Monetary Fund, to be an honest broker here. So I'm going to use the numbers from the IMF. And the IMF says that the global fossil fuel industry is currently subsidized at about 5.2 trillion per year, or about 6.5% of global GDP per year. And they also say for the US that the US government subsidizes the oil industry, the fossil fuel industry, by about 650 billion per year. Now, does the US write a check to the ExxonMobil or other companies for 650 billion a year? No, of course not. But those companies do receive tax breaks and subsidies that amount to, according to the IMF, about 650 billion per year. And that's things like writing off the cost of drilling, writing off the cost of oil field depletion allowances and things like that. And there's a big question about why these are some of the richest countries, some of the richest companies in the world. Why should the US government subsidize them with these tax breaks? And the answer is, well, it started out back in the 70s when we had the oil crisis. And I think all of you remember the oil crisis in the 70s when suddenly we woke up and Saudi Arabia was holding us hostage, and we suddenly realized we were highly dependent on foreign oil. And so, Congress said, we've got to turn that around. We've got to become net producers of oil. And so the way to do that is we got to build all these tax incentives into the code that are going to into the tax code that will incentivize the oil industry to drill in this country and produce oil here right at home. And it worked. The United States is now a net exporter of fossil fuels. It worked. But the question is, do we still need it? Given the fact that, again, these are some of the richest companies in the world, do the U.S. taxpayers still need to be subsidizing them at the rate of 650 billion a year? What if we just reduce it by a factor of 2? That would be more than enough to deal with climate change, given the numbers up here. So just want to let you think about that a little bit. And finally, I want to mention another tool in the toolbox here called carbon pricing. Carbon pricing is an important policy tool for addressing the climate crisis by providing the public with a pricing incentive to bring fossil fuel use down. It generally places a tax or a fee on fossil fuels at or near the point of production and returns some or all of the revenue to consumers, such that those who are heavy consumers of fossil fuels lose money, while those who are light consumers of fossil fuels make money. The taxes and fees go up over time to increasingly discourage fossil fuel use. Generally includes exemptions for certain sectors, such as the military and agriculture, and tariffs on imported fossil fuels. Now, there are currently 10 different carbon pricing bills moving forward in Congress. Not going to talk about them in any detail, but I do want to highlight two of them. The first is the Energy Innovation and Carbon Dividend Act. And that is the thing that's sort of the granddaddy of them all that got this whole thing rolling. And that is the bill that is sponsored by Citizens Climate Lobby, of which I'm a member. And that kind of laid out the groundwork for this. It's based on Nobel Prize winning economics and analysis. It's actually been implemented in Canada a couple of years ago. And that kind of was the thing that got the ball rolling. But the other one I want to mention is the CAR Act, the Climate Action and Rebate Act. And that is sponsored by Congressman Panetta. And oh, by the way, I want to put in a big plug for Congressman Panetta. We are very blessed to have him as our representative. He's a real leader in the Congress on climate change. He's a member of the Climate Solutions Caucus. He's working really hard to work across the aisle and get support from the Republican side. He's also working very well with the senators, with the Senate. He has a co-sponsor with Senator Coons here. And I personally like the CAR Act. I've looked at it in detail, and it has a lot of big advantages there. So good on Jimmy Panetta for pursuing that. Well, going to make some closing comments here. You're probably wondering, what can I do as an individual? Well, you can learn the basics of the science behind why our planet is warming and the climate is changing. And you've taken a big step here tonight by suffering through my talk. You can do what you can to reduce your carbon footprint while still living the life you want to live. You can join an advocacy group such as the Citizens Climate Lobby and participate actively. And I can tell you, we have a very active Monterey chapter, and we'd love to have you join. You can just Google Citizens Climate Lobby, join the national chapter, put in your address, and we'll find you and get you on our email list. It's free to join. Whenever you have an opportunity to interact with a leader in your community, be they political or otherwise, let them know that you want to see action taken on this issue. Become a leader in your community on this issue. And I know some of you are, and that's fantastic. And finally, vote for candidates who will address your concerns about climate change. And then finally, I'm going to call on the greatest naturalist of our time, Sir David Attenborough, and a few others to make some final closing comments, and then we will open it up for questions and discussion. So here we go.
Standing here in the English countryside, it may not seem obvious, but we are facing a man-made disaster on a global scale. In the 20 years since I first started talking about the impact of climate change on our world, conditions have changed far faster than I ever imagined.
Before we started to burn coal, the amount of carbon dioxide in the atmosphere was about 280 parts per million. It's now over 400 parts per million. And the planet gets warmer and warmer.
We are seeing the impacts of climate change now play out in real time. They're no longer subtle.
We're not just talking about an inconvenience. We're talking about people's lives, their livelihoods, and their communities being damaged. Join the dots. It's happening. It's happening in your world. It's happening in my world. And let's be very clear about this. It is going to get much worse.
It may sound frightening, but the scientific evidence is that if we have not taken dramatic action within the next decade, we could face irreversible damage to the natural world and the collapse of our societies.
There are thousands of scientists around the world in almost every single country working to understand what will happen in the future if we don't act, we don't do more. They predict that if we carry on as we are now, where CO2 continues to increase, we would hit 1.5 degrees global warming by between 2040 and 2050.
We're on course to go through 1.5 degrees in just a few decades' time, and the models differ slightly as to exactly when. And not long after that, we're on a trajectory to go through 2 degrees.
It really becomes difficult to see at such levels of warming how we're going to maintain our agriculture such that the population of the world can actually feed itself.
And ensuring people have access to clean, safe drinking water will become much more difficult.
Developing countries that are at the front line of this battle.
those parts of the globe which will suffer the most and the soonest are not those parts of the globe which have actually loaded all those carbon dioxides in the atmosphere in the first instance.
But you have to understand this is also a crisis for the world. The fact is that if the poor are suffering today, then the rich will also suffer tomorrow.
We're running out of time, but there is still hope.
It's actually not that complicated. We need to shift our energy system away from fossil fuels that produce greenhouse gases and towards renewable energies that don't.
We still have time to turn everything around, to pull the emergency brake and to take action. But that short period of time isn't going to last for long.
There's a message for all of us in the voices of these young people. It is, after all, their generation who will inherit this dangerous legacy. We now stand at a unique point in our planet's history, one where we must all share responsibility, both for our present well-being and for the future of life on Earth.
Okay, that's it. I'm going to stop sharing my screen now and go back to gallery view and take some questions. Okay, it looks like Jeff has a question there. Want to unmute Jeff? Can you unmute Jeff? There you go.
Okay. Where can we get, you mentioned copies and things. Can we get a recording or a disc, a CD disc of what you just presented to us?
Yeah, what I'm going to do is I have a YouTube channel, and I'm going to, within a few days, I'll edit this down and put it on my YouTube channel, and then I'll send Sis the link to it, and she can just send that out to everyone, and you can just click on that link and see it. You can play it back on YouTube.
But how can I get it from YouTube to a CD, something I can carry around?
Okay, I can do that. I can do that for you. So if you just send me an email with your address, we can get that going.
Okay, great. Thank you.
And Sis has my email address.
I had a question. This is John.
John, yeah, I see that.
It's directly related. Is there any copyright restriction? I want to send it to an organization that has a satellite broadcasting service in East Africa, and they would love to have this video to show.
I don't see any problem with that. Yeah.
Good. Great.
Any?
Again, maybe send me an email if you need it on a CD, and we can work it out that way.
Okay. Thank you.
Mm-hmm.
Hi, I've got a couple of questions or comments.
Yes.
One is, I understand that some scientists are working on improving nuclear power plants to more safely and efficiently generate power using nuclear energy. And that, of course, would not put carbon dioxide into the atmosphere. So that's one interesting thing you might comment on. And another is, I understand that one of the results of the chaotic effects of climate change is the effect on the jet stream. And I was wondering, how important that is. And for instance, in this terrible recent episode extending extremely cold weather clear down into Texas and all, if that isn't a result of the jet stream becoming chaotic and kind of bending southward, bringing very cold air south as a result. Mm-hmm. Could you comment on those things?
Yeah, those are two fantastic questions. I love to talk about nuclear power. I'm not a fan of nuclear power, so I'm going to give you a biased viewpoint there on nuclear power. I think what you might have been talking about is there's been discussion about thorium reactors. So there's a material called thorium. It's like uranium. It's fissionable material, and there has been proposals to produce thorium reactors to replace the current generation of uranium-based reactors. A thorium reactor is inherently safer than a uranium-based reactor for a number of reasons. But I don't think anything is. My contention is anytime you have something that's a complex hardware, software, and human or system, a failure at some point is inevitable. You wait long if you're going to have a failure. But nevertheless, the thorium reactors are inherently safer than uranium reactors. Number one. Number two, they don't produce as much nuclear waste as the uranium reactors, and the nuclear waste doesn't last as long, so that's another advantage. So what's not to love about thorium reactors? Well, 50 years ago, the nuclear power industry had the opportunity to go down the thorium route or the uranium route, and they made a decision to go down the uranium route. And the reason they did is because the power from uranium reactors is much more cost effective than thorium. There's a lot of thorium out in the world, but it turns out that the breeding cycle in a thorium reactor is much less efficient than the breeding cycle in a uranium reactor. And as a result, the resulting nuclear power will be much more expensive. Well, it turns out electricity from nuclear power now from the uranium reactors is by far the most expensive. It's like 4 or 5 times more expensive than wind power. And that's one reason why it's kind of getting priced out here. And finally, there's another problem, and that is in the case of thorium reactors, just like uranium-based reactors, if you own a thorium reactor, you have a path to nuclear weapons. That's exactly how North Korea has obtained their arsenal of nuclear weapons. They have reprocessed their spent fuel rods into weapons-grade plutonium, and now they have an arsenal of about 30 to 40 nuclear weapons. That's exactly why the Israeli Air Force acted twice, once in Iraq and once in Syria, to take out nuclear power plants because they feared that those countries were going to produce nuclear weapons that would be used against them. So if we had a proliferation of thorium-based reactors in the world, yes, they would be safer than uranium-based reactors, and yes, they would not put any CO2 into the atmosphere, and that's great. We'd still have a nuclear waste problem, but not as bad. But we would still have a nuclear weapons proliferation problem. In fact, it's even easier to make nuclear weapons from the output of a thorium reactor. And it could be done covertly too, by the way. That's the real concern. One could take a thorium reactor and covertly derive from it uranium 233, which is weapons grade material, and produce nuclear weapons. And inspectors could come in and do it right under their noses. They wouldn't know it. All you would need would be a university kind of laboratory. So I'm not a big fan of nuclear power. I'm not a big fan of even thorium-based reactors. There are no power plants in the world currently based on thorium. There are a number of countries are doing research. They have research thorium reactors. China has announced plans to put 2 thorium power plants into operation by 2030. Whether they carry through on that or not, who knows? But they have announced plans to do so. So we'll see if that happens or not. France is big on nuclear power. They're the one country in the world that's going great guns on nuclear power. But the other countries in Europe are not. Just as France is building out its nuclear power plants, Germany and UK and other countries are decommissioning them. We are decommissioning plants in our country. But having said all that, I'm a big fan of Project Drawdown, and Project Drawdown does include nuclear power as one of their solutions, but they see it as an interim solution, not as a long-term solution. They say it's an interim solution until we can really get green energy renewables going. We need nuclear power for maybe another few decades, but not as a long-term solution, and I agree with that. Now, the thing about the jet stream, that's a great question. And I'm going to go back to my screen share here because I've got a slide on that. So hang in there with me, going back to screen share. And let's see if we can get to where I need to get to.
Standing here.
And hang in there with me for a second here. And because what you're talking about is sort of the polar vortex. This is what we're talking about here. And what we're looking at here is summer, winter. This is called the Arctic Oscillation. In the summertime, the jet stream is very tightly packed, very fast. There's a large temperature contrast, and it keeps all the cold air really bound up over the Arctic. And we have a nice warm summer down here in the United States. In the wintertime, there's a small temperature contrast across the jet stream. Sorry. And with that small temperature contrast, the jet stream becomes weaker and it meanders more, and you get more of this meandering. Now, there is a theory out there that as the polar regions warm faster than the lower latitudes, that's yielding a more wavy jet stream. And when you get that waviness, when it goes down to the south, that's called a trough. You get these cold air outbreaks. That is, at this point, a theory. It's not really a part of the accepted science at this point. It may be true, but there isn't a scientific consensus on whether that's true or not. So we'll have to see if that pans out. But what I said earlier, I believe is part of the scientific consensus, and that is as we experience this climate change, storms are getting stronger, and that means winter storms as well as summer storms. And when the winter storms get stronger, then they bring colder air down, and you get these cold air outbreaks. Notice that, very often when we get something like this happening, you have freezing temperatures on the East Coast, people will be saying, well, gosh, where's your global warming? Well, the point is you have that cold air here, but you have warm air in this ridge here. Very often, we'll be experiencing beautiful, summertime like conditions here. In the wintertime, they'll be freezing on the East Coast, and that's because you have this pattern in the jet stream. And when you do the average all around, it kind of averages out. So, anyway, the bottom line is I'm glad you brought that up. And what I'll say on that is it is a hypothesis at this point that climate change is producing a wavier jet stream, but it hasn't really been confirmed and become part of the scientific consensus at this point. Okay, more questions?
I see a question. Oh, I just lost it from
Brian?
Ned Lesnick. Okay. Brian, go ahead.
Thank you, Mr. Clancy, for all of this. And
Sure.
I want to make a leap into a question that I'd like to focus on Del Mesa. There are questions in which we're discussing right now amongst the organization of solar panels, reduced water usage, and protection from around the fire zones and all. And maybe with the transference away from natural gas, everything that we've got, and maybe to all electric. Is this, could we be considered that this is on the right path, or is this just pie in the sky stuff that we shouldn't even bother with?
Absolutely on the right path. Solar is just taking off like mad, and it's getting more and more cost effective, more efficient, and we have tremendous solar resource here in this part of California, and that's something I strongly would recommend. I've had talks at another place in Carmel. It's right on the tip of my tongue. I can't remember it. And they have a similar project going there. They're looking at solar panels and that sort of thing. Reducing the water usage is also good. Water is a big part of climate change, and of course we do expect, unfortunately, that we're going to see continued drying, continued problems with wildfires, continued problems with smoke from distant wildfires. Unfortunately, that's in our future as we go forward. So taking steps to protect your facility from wildfires absolutely is a good one too.
Mike, there's a question I'll read to you in the chat room. And I think this will be our last and then I'll close after you respond to this. This is from Ned Lesnick. Over the next decade, what is the forecasted amount of CO2 being generated by China, India, and India, and what are their financial commitments under the Paris Climate Accord? How many coal-fired power plants come online each year in China and India?
Yeah, I don't have the specifics of those numbers, but I can talk about it in general terms. China is really a mixed bag. They are investing more in renewable energy than any other country. They are bringing on more windmills and solar than any other country, but they're also bringing on more coal-fired power plants as well. And in fact, when you look at all the coal-fired plants they're bringing on board, their percentage of green energy may be going up, but still their emissions are going up because they're bringing on so many coal-fired plants. The bottom line in China is they are very, very energy hungry. And yes, they're investing in renewables, but they're also investing in coal-fired plants. And of course, coal is the dirtiest burning fossil fuel. It's much better to burn natural gas than coal. But China has a lot of coal, and they are energy hungry because they're trying to raise the standard of living of their people, and that's going to be a real challenge. In terms of the commitments. And India, I think, is very similar. Again, they're trying to bring up the standard of living of their country, and the way you do that is through cheap energy. And they've got a lot of coal-fired plants going there as well. In terms of commitments to Paris, the thing about Paris is kind of a voluntary thing. It doesn't really have teeth. It's kind of peer pressure, and everyone kind of sets targets and gets together and talks about how well they're doing. I think China has been playing actively, and I think I can't tell you the details there, but I think at least they stayed in the accord, and they've been participating. But in general, as of this moment, going back from the time when the accord was signed to where we are right now, the entire world has fallen behind where we need to be. And the more you fall behind, the harder it is to catch up. It's a cumulative kind of thing. So in terms of those kinds of numbers, I probably can find a report to send to you that might allow you to find some of that information out, but I don't have it at my fingertips.
Thank you. And I'd like to take time now, Mike, to thank you so much. Your presentation was fascinating.
Well, thank you.
It was also frightening, I'm sure, to everyone who was listening. Very thorough and comprehensive. And what you've done for us has given us lots to digest. And so I'm sure we'll be walking around thinking about all of the different things you've talked about, but it was an amazing presentation. And I don't know where we'll start in our thinking, but I'm sure we'll all start from a different point somewhere along the line. But thank you. We appreciate your coming. You've done a fabulous job. And we want to thank you for considering us in your busy life.